So now that we know how to find the multiplicity and we can factor something and just state what the multiplicity is, we need to talk about why we care. So what's the big deal about multiplicity? Okay, multiplicity is going to tell us about how a graph is going to act, how it's going to behave as it approaches the x-axis. So what we know is as we get close to that point, we know it's not just necessarily going to go straight through the point. It might bend or turn or bounce or something like that. So let's take a look at what we mean. Okay, so if the 0 has a multiplicity of 1, and that's what we assume when we don't state what the 0 is, right? So if we just say, for example, something like, here's a 0, x equals 7. That's the 0. Because it has a multiplicity of 1, which we know because it's not stated, I'm going to go over to x equals 7. I'm going to put down a point, and I know that this is going to act like a straight line as it travels through the point. Okay, so we know that everything with a highest exponent of 1, when we graph it, we call those linear functions. This is linear, okay? Highest exponent of 1 functions are linear. Every single one of those is a straight line. So what we're claiming is that at the point x equals 7, which is our 0, that when the graph goes through that point, it's going to go through and look like a straight line, okay? Just in that little space right around the x-axis, okay? If we now turn it into something like x equals 1, okay, but I tell you that there's a multiplicity of 2, what we're claiming is that if something has a multiplicity of 2, the graph is going to turn away from the x-axis just like a parabola does. So we know things that are quadratic, which is what we call quadratic, is what we call something with a highest exponent of 2. Those things look like parabolas, right? They look like this. So we're claiming that if I graph x equals 1, and I know it has a multiplicity of 2, that what's going to happen is that as our graph approaches this point, it's going to act like a parabola, and it's going to turn around, right, and make that U shape. So in this case, it might look something like this. Okay? And again, it's only in the little space right around the point. Right? The rest of the graph can do whatever it wants, but we just know right near x equals 1, because it has a multiplicity of 2, that it's going to act like a parabola. Okay? And so you can probably assume that something like x equals -6 that has a multiplicity of 3 is going to act like a cubic function, which is what we call functions with the highest exponent of 3. And if you remember, cubic functions kind of look like this. Okay? So they're kind of like pretty straight up, and then they make a sharp turn, and then they go pretty straight up again. So if I were to graph x equals -6, okay, I know that just close to that point, I'm going to end up with, pretty straight down, okay, and then it's going to make a sharp curve, and then it's going to go pretty straight up, right? And again, all the rest of it can be whatever it wants. Okay? Obviously, we also have to think about things like end behavior and coefficients, which might flip any of these, but this is the basic idea. This is what a multiplicity 3 looks like. This is what a multiplicity 2 looks like. Multiplicity 1. Anything higher than this is going to act like one of these, but maybe a little flatter, okay, or a little sharper, depending on what the exponent is. So let's take a look at an example and see how this is showing up. So if I have this problem and I say, there's some function h of x, and it has zeros at -2 and 4, and for each of these points I'm saying x equals -2 has a multiplicity of 2. X equals 4 has a multiplicity of 3. Okay? Here's what we're going to say. We're going to sketch this like we normally did. When we sketched, we needed to know about the degree. Okay? In this case, it looks like it has a degree 2. I'm getting 2 zeros from x equals -2. I'm getting 3 more from x equals 4. So I'm going to say there are 5 zeros when I count all the duplicates. So this is a degree 5. Okay? An odd degree, okay, has a down up, okay, end behavior. Okay? And it's going to stay like that because our lead coefficient's positive. I have no reason to change it from down up to up down. That would be if I had a negative coefficient. So in this case, I know this has down up end behavior. So let's put down these points. I have x equals -2 and x equals +4. Okay? I know that coming out of -2, it needs to be traveling down. So I'm going to put a little down arrow here, kind of just in this space. So I know that it's going to be heading down when it comes out of that end. And coming out of x equals 4, it needs to be heading up. Okay, and I know that because a degree 5 has to be down up when we finish. Okay, so here's where things get a little bit different. Because x equals -2 has a multiplicity of 2, when the graph gets close to -2, it's going to act like a parabola, which means it's going to turn, hit -2, and then bounce down, okay, and start heading the other direction. Parabolas, right? Degree 2s look like parabolas, and so now at -2, it looks like a parabola. Okay, and so I can do the same thing. I'm going to say eventually this is going to have to head back up to 4, and here's the way it's got to look at 4. A cubic function kind of goes straight through, but then it's got a sharp turn at the end of it. It's got a sharp turn that heads back up. Right? So a cubic function would look like that, which means I'm going to need some other kind of curve in here to connect those two pieces together. So I know my graph looks like this. It's got a multiplicity of 2, so it's got a quadratic behavior, a parabola behavior at -2, and it's got a multiplicity of 3, which means it acts like a cubic when we get to x equals 4. Okay, so this would be a rough sketch of what it looks like. Obviously, we don't know, for example, how low this turn is. It could be way down here. We don't know where this crosses the y-axis yet. It could go way down here before it comes back up. But we know at the zeros, at the endpoints, that it should be acting like a parabola and it should be acting like a cubic function. Okay, so let's take a look at one more of these. Okay, this was the same basic idea. I'm giving you the zeros. Okay, and when I look at this, I'm going to count my zeros and say it looks like 1, 2, 3, 4, 5. This is also a degree 5 polynomial. Okay, I'm counting how many zeros I have with all of the duplicates counted. Because my lead coefficient is negative, I'm going to say this has up-down end behavior. Okay, so when I put my points down, I'm going to say -6, okay, -1, and +3 are my zeros. Okay, I know that it needs to be coming out of the very left-hand side, going up, and it needs to be coming out of the very right-hand side, heading down. Okay. So I know that it's got to look like that. It looks like at -6, it has no statement about multiplicity, so it's going to act like a straight line. It's not going to make any bends or turns going through. It's going to do something just like that, straight line. Okay. At both -1 and 3, it needs to act like a parabola, which means when it hits those points, okay, it's going to bend like a U-shape. Same thing here. It's got to bend like a U-shape. And if this one's heading down, I know it's got to be under the x-axis like that. Okay? So I just need to really connect these together. I know there's going to be a turn to head back up towards this parabola. Right? And I'm going to have to turn again to head back up towards the other parabola. And so it's going to look something like that. Okay? And again, we don't know how low these points go. Right? We have to do that at a separate time. That's a whole other lesson. Right? But the idea is that we can at least determine at the zeros about how the graph is going to look. Okay, so let's take a look at a couple more examples. Those are some for you to try. They're very similar to what we've done. So let's take a look at an example where maybe they didn't give me the zeros. They didn't make a statement and say, hey, here it is. They just said, here's the factored form of the polynomial, and they want to know the x and the y intercepts and a rough graph of the function. Okay, so again, we have to do a rough graph because we don't know about all the highs and lows. Right, but we can at least get the x-intercepts down, the y-intercepts down. We know how the end behavior is going to be. We know how the graph is going to react at all of those zeros, and we're going to get all of that onto this graph. Right, so we're going to start off with the x-intercepts. The x-intercepts are what we've been calling the zeros. They are the same thing. So I know that x minus 4 is going to produce a 0, or it's going to produce an x-intercept, which is 4. But I know this 4 has a multiplicity of 2, and that is because I have duplicate x minus 4s, and I know that because of the exponent. Okay, I'm also going to get a 0, okay, from x plus 1, which is going to be in this case -1, and that has a multiplicity of 3, and I know that because it's got a highest exponent of 3. Okay, so this looks like a degree 5 polynomial. Okay, a degree 5 polynomial again. Okay, degree 5 will have down up end behavior. And I know that because I can actually look at the lead coefficient and say, here's where the lead coefficient would be if there were any numbers. There's nothing there, so it's positive. Right? So I'm going to say, in this case, let's put x equals 4 down. Okay, there it is. Okay, let's put x equals -1 down. Right there. Okay, and I can, again, sketch pretty accurately what it's going to look like at these points. So I know coming out of the very left-hand endpoint, it's got to be traveling down. Okay. I know coming out of the very right-hand endpoint, it's got to be traveling up. Okay. I know that at x equals 4, it's going to bounce. Okay. It's going to act like a parabola, and it's going to pretty much come down and turn like that. Okay. And I know at -1, because it has a multiplicity of 3, that it's going to kind of go like this. Okay. It's pretty straight there, and then it's going to make a sharp turn down, okay, and a sharp turn up. Okay. So that's kind of taking all the multiplicity and the end behavior into account. So we have one new little piece of information here. Here's the new thing. We can calculate y-intercepts. We haven't done it with polynomials yet, but we know how to do it. Every y-intercept is just plug a 0 in for x, tell me what happens. So let's see what happens. Okay, so if I plug in go up to my function r of x, I'm going to say, okay, that r of x is equal to, okay, when I plug in a 0, here's what I get. Okay. Well, 0 minus 4 squared is just negative 4 squared. Well, negative 4 squared is 16. Okay, this is being multiplied by, okay, 1 cubed, okay, which is 1. So when I plug a 0 into this function, it looks like I'm getting back 16 times 1, which is 16. So I'm going to call this r of 0 because we plugged in a 0. Okay, and when I plug in a 0 and I simplify the expression, I get a 16 back. Okay, in order to fit that 16 on this graph, I'm probably going to have to count by 2. So let's count by 2s. 2, 4, 6, 8, 10, 12, 14, 16. That would be right here. Okay, so it's okay for you to scale your graph counting by 1s on the x-axis and 2s on the y-axis, and that's what we had to do. So what I know about this a little bit more accurately is that before this thing gets to the y-axis, it needs to head up very sharply, hit at 16, and then it can come back down and approach this graph like a parabola. So I would say this is a pretty accurate graph of what this function is going to look like, taking into account end behavior, multiplicity, and the y-intercepts, right? So this is as accurate as we can get, and it's a pretty accurate graph of what this r of x is going to look like.